Okay, everybody. Today we're going to be discussing freezing and boiling points. I know you hate these ed puzzles where I record myself, so this one's going to kind of be brief. It's not going to be as long as the last one, I promise. There's not going to be as much work involved, but I still encourage you to write down the notes for these slides. I encourage you to pause where you need to pause to make sure you have all the notes written down that you need to, because notes on freezing and boiling point depression are going to help you moving forward on homework assignments and just to understand the content a lot better. At this time, I'll go ahead and warn you there is math in this presentation, so you will need to go grab a calculator. So pause the video at this time, go grab a calculator, return to your seats, and then start the video again once you have the calculator and you're ready to do some math. All right, so the first concept we're talking about today is a concept called the freezing point depression. The freezing point depression tells you the change in temperature of a solvent when a solute is added to the solution. A lot of vocabulary words there. Remember, your solvent is the thing that does the dissolving. It's usually water. A solute is the thing that's being dissolved, and then your solution is the combination of solute and solvent. So your freezing point depression tells you how much the temperature is going to change whenever you add a solute into a solvent. A good example of this is if you have something like water. Water, our most common solvent, we know that it freezes at 32 degrees Fahrenheit or 0 degrees Celsius. Now, if we were to add something to the water and dissolve it, like sugar or salt or any form of chemical, the freezing point's no longer going to be 0 degrees Celsius or 32 degrees Fahrenheit. It's going to change depending on various chemical factors, and we're just going to solve those factors. We don't have to get into the deep chemical concepts behind why it occurs, but we're just going to solve and figure out what the temperature is going to change to, what the new freezing temperature is. The equation we're using for that is TF equals negative IKFM. I'll explain those variables here in a second. The really important thing to focus on is there is a negative in this equation. So lots of your answers are going to show up as negative when we're dealing with freezing point depression. When we get to the boiling point equation, there is no negative in that one. So that's the biggest difference between freezing and boiling point. So this equation has a negative in it. TF is going to represent your change in freezing point of the solution. This is your temperature. This is in degrees Celsius. TF is not always going to be your answer in the question. For instance, if I tell you that the freezing point of rubbing alcohol is negative 10 degrees Celsius, and you solve for a TF and it gives you negative 4, and I ask you in the question, what is your new temperature going to be? Well, your change of temperature is negative 4. Your starting freezing point was negative 10. So negative 10 with a negative 4 added to it means your new freezing temperature will be negative 14. So there's an example of how that might be used. Your I is your Van't Hoff factor. This tells you the number of ions when a solution is dissolved. We know from, I believe it was Unit 5, we were talking about different ions when we're forming chemical compounds. The most common ions we talk about are sodium chloride, or NaCl. When we talk about NaCl, I'll see if I can write this on the board for you. So we have NaCl. Our Na has the positive charge. Our Cl has the minus charge. So we have a cation there and we have an anion there. That means we have 2 total ions. So in this case, our Van't Hoff factor would be 2. If we're dealing with something like NH3, which is ammonia, NH3 is a covalent compound. So covalent compounds don't have ions. And so that would just be a 1. It is its own ion. We don't separate the N and the H3 from each other. So you'll have to kind of remember back to what a ionic bond is versus a covalent bond. But things that involve metals and nonmetals on your periodic table are generally going to be your ionic bonds, and those are going to have your Van't Hoff factor of 2. So if the question was using sodium chloride, your Van't Hoff factor is 2, because we have an Na with a positive and a Cl with a minus. If we're dealing with a covalent compound, which is 2 nonmetals, our Van't Hoff factor is likely going to be 1. Our Kf is a constant. I'm usually going to just give that to you in the question. The only time I won't give you a Kf is if I'm asking you to solve for the Kf, which is just a little bit of algebra at that point. And then M is your molality. We talked about the last couple of days. Molality, moles per kilogram. And again, that will probably be given to you in the question. I don't think I'll make you solve for molality before doing a freezing point depression. All right, let us erase these, and we'll get into solving this question. So our first practice problem, I'll give you a second to see if you can try solving this one. The question is, what is the new freezing point of an aqueous 1 molality NaCl solution if the normal freezing point is 0 degrees Celsius? And I've given you your Kf, which is 1.86, and the units are degrees Celsius over molality. So I'll give you a couple minutes to try solving this one. Put your answer on your Edpuzzle, and then we'll work through it together. Cool. So I'll remind you first of your equation. Your equation here is Tf equals negative I Kfm. We can write out what each variable is here. So our Tf is what we're solving for. Our negative I, we're going to have 2 there. And it's 2 because if we remember here with our sodium chloride, we have our NaCl. Na has a positive charge. Cl has a negative charge. That means we have this ion right here, that's one of them. And we have this ion right here, which is 2 of them. So we have a total of 2 ions. That's why we've written 2 right here for our Van't Hoff factor. Our Kf is what I gave to you in the equation here, which is 1.86. And then our molality is 1. Again, I've given that to you in the equation. So we plug everything in. Tf equals negative 2. Don't forget your negative sign when doing freezing point depression. Negative 2 times 1.86 times 1. It should give you an answer of negative 3.72 degrees Celsius. Now that is how much your temperature changes. It's not necessarily your new freezing point. In this case, it will be, but it's not necessarily your new freezing point. If we're trying to figure out what the new freezing point is going to be, what we do is we take our starting freezing point, which is right here in the question. We would take our 0 degrees Celsius minus whatever our Tf is, minus 3.72. So our new freezing point is going to be negative 3.72 degrees Celsius. And that's solving for the actual freezing point. If I ask you what the freezing point depression is, you're just going to stop at this spot right here. next concept we talk about is going to be the boiling point elevation. This is basically the exact same thing as freezing point depression, except boiling point elevation relates to how the boiling point changes. So our boiling point elevation tells you the change in temperature of a solvent when a solute is added to solution. Again, if we take water, for example, for all of you who've ever made spaghetti at home, lots of the time, and if you don't do this, I don't know if it makes a difference or not. It's your call. You're supposed to add salt to the water when you boil it because it changes the boiling point of the water and causes the temperature overall of the water to change when you boil it. So there you're adding a solute into, which is salt, into your water, which is your solvent, and now the boiling point of your new salt water is going to change, and that's supposed to help your pasta cook better. Our equation for this, TB, B stands for boiling point, TB equals IKBM. Exact same equation. The difference with boiling point is it's going to be positive, so we don't have a negative sign in the equation. Everything represents the same thing here. I realize I've made a little typo here. This is not supposed to be a negative I. I'm going to go ahead and get rid of that negative sign the best I can. That's supposed to be a positive I. So in the equation, TB is your change in boiling point of a solution. It's going to be in degrees Celsius. Positive I, again, is your Van't Hoff factor. This tells you the number of ions when a solution is dissolved. KB is your constant. Again, I'm going to give that to you in the equation unless I'm trying to get you to solve for that. And M is your molality, moles per kilogram. Cool. Got another practice problem for you to do. This will be our last practice problem on the Edpuzzle. I told you this was a lot shorter. Not trying to torture you too much. Our question here is, what is the boiling point elevation of water when a 3.3468 molality solution of water and ammonia? That's kind of horrible grammar, but we're going to roll with it. I've given you the chemical equation of ammonia. I've given you the KB, and I'm asking you what the boiling point elevation of water is going to be with these. So I'll give you a couple minutes to solve that, put your answer in the Edpuzzle, and then we'll work through it together. Awesome. So I'm going to start again. Here's our equation. TB equals IKBM. We know what those represent. We're going to write out what those represent. TB is what we're solving for, boiling point elevation. I, which is our Van't Hoff factor, is going to be 1 here. The reason our I is 1 here is because we have NH3. NH3 are 2 nonmetals, and 2 nonmetals coming together form a covalent bond. And if it's a covalent bond, your Van't Hoff factor will be 1 because they don't break apart into ions. They kind of stay together. So that is why our Van't Hoff factor is 1, because covalent bonds don't break apart into ions. Our KB given to you in the question is 0.52, and then your molality, again given to you in the question, is 3.3468. So what we do here is we are going to multiply. Remember, this is positive because we're doing boiling point elevation. So boiling point elevation equals 1 times 0.52 times 3.3468. So you put that in your calculator, you are going to get 1.74 degrees Celsius, which means by adding ammonia to this solution of water, your boiling point will increase by 1.74 degrees Celsius. If you wanted to work farther on this, we know that the boiling point of water is 100 degrees Celsius. It's just common knowledge. I didn't give that to you in the question anywhere. Our boiling point is changing. It's increasing by 1.74 degrees Celsius. So if I asked you what the new boiling point would be, you would do 100 plus 1.74, which would be 101.74 degrees Celsius. So the biggest takeaway when we're talking about freezing point depression and boiling point elevation is in our equations, our freezing point depression is going to have a negative sign beside the I, and in our boiling point elevation, there is no sign beside the I. If you have any questions about how to solve freezing point depression questions or boiling point elevation questions, jot it down somewhere. We can talk about it on Monday, or you can send me an email if it can't wait, and I'll email you back as soon as I can with a little further explanation to try to get you to understand this. But this is all I have for you today. Make sure you submit your Edpuzzle completely, and enjoy the rest of your day.